So welcome everyone to pick 2 of this week's IQS seminar. I'm happy to present Dominic Briseno Colunga, who is a graduate student here in the Math, Physics, Philosophy Doctor of Science program. I've known Dominic for quite a few years at this point. He did his undergraduate here at Chapman University, but in computer science, and then discovered that physics is his true passion. His senior year, changed tacks and learns the entire physics curriculum in about a year during his master's program here in the Computational and Data Sciences program, and is now working on his Doctor of Science in the MPP program. So without further ado, Dominic, take it away.
Hey, first of all, thank you everyone for your patience. I was very embarrassed about the snafu yesterday, but I really appreciate the opportunity to restore my slides to what they were instead of having to give an ad-libbed presentation. So I really appreciate everyone's patience. So today I'm going to talk about dynamical stabilization, or a method to dynamically stabilize a two-level system, a qubit, and the manifolds or surfaces of high lifetime of good stability that come out when you drive it in a specific way, which I will introduce later.
I like dynamical stabilization.
I'm trying to scale back the physics jargon a little bit.
The concept of dynamical stabilization is very nice.
Yeah, I think it's more intuitive than bichromatic. Okay. So first of all, a little motivation as to why we're even looking at this. So I work with superconducting circuits, and they have emerged as one of the leading, if not the leading candidate for long-term scalable quantum computing. Why? Well, they are circuits that you can build and you can fabricate them. So you have the ability to choose which circuit components, what qualities of the circuit components you are building. It's very configurable, like you're building your own configurable atom. And the other benefit to them is that they are big. They're not atomic in scale. They are macroscopic objects. You can actually see them with your eye if you have good eyesight. And because they are macroscopic objects, they couple really, really well to control fields, control particles. This enables us to build fast, high-fidelity operation on these chips that are orders of magnitude, many orders of magnitude, faster than are possible on any other architecture. And this is extremely important because in the long term, we are planning on running billions of operations on these chips for a single application. So those linear factors of how long it takes to run each application, even though they don't affect quantum advantage per se, they matter a lot. But they have very serious problems. And the problems mirror their benefits. So a pro of the superconducting circuits is you can configure them. A con is that they are configurable, which means that they are also sensitive to unavoidable variance during fabrication of the chip. Speak to any experimentalist that works in this, and the first chip that they manufacture is probably not the one that they're writing their paper on. It takes many, many iterations and debugging to try to get these chips to be exactly right. And even when you get them as close as you can to being right, you will not nail the parameters that you're trying to get.
But sorry, this is only a question of the way in which you artifact the object.
Yes.
Or could be also a question concerning the material that they are using, the material as.
Yes.
That is not under your control.
Yes. Basically, if you can think of a way in which this could go badly, it will go badly that way. It is difficult. This is difficult. They have very strong advantages. They are very, very fast, but it is difficult to use them. They are a touchy system. They are very difficult to manufacture. So but regardless of these pretty big downfalls, that the ability to actually conduct these quantum operations at such a high fidelity so quickly is such a large benefit that they continue to be the leading candidate for superconducting for quantum computing. So much of the research in superconducting qubits is pointed at designing new circuits that are resistant to different types of noise and learning how to control them so that you have less noise-induced data loss. One of the most recent iterations of these configurations is called the Fluxonian, which is a frequency tunable, which means that you can tune the frequency of the oscillations, which actually happen inside of the circuit, qubit that is a flux qubit, which means that most of its energy and most of its controllability lies in its degree of freedom in its magnetic degrees of freedom, or in the magnetic field that the circuit effectively stores. Because it is biased to being controlled through its magnetic field, it is inherently resistant to charge noise, which is much more difficult to mitigate than magnetic flux noise. Also, the fact that we have this control knob, which allows us to tune the frequency of the qubit, is a huge benefit because then we are not married to the attributes of the qubit that we manufactured in the first place. We can now tune and change the properties of the qubit with a control protocol rather than having to nail it in fab on first try. But because it is biased towards being controlled through its magnetic field, it is also extremely sensitive to a type of flux noise called 1/f noise, which is ubiquitous. You cannot get rid of it. This leads to very, very, very short lifetimes of the qubit, except for certain values of this tunable flux, at which the circuit becomes mostly resistant to this 1/f noise. But
Sorry, when you say cubic tuning, the process of tuning is a manual process or is controlled by another computer? So there is a way to control it by a program?
Sure, both. I mean, you can literally go into the lab and turn a knob, and it will send a signal to a waveform generator that will tune flux inside of the chip. But you can also design control protocols, which is actually what we're looking at right now. You can design control protocols that are automated that will modulate the frequency of the qubit. One important detail about the values at which this becomes invariant to or resistant to flux noise is that they are separated and discrete. So really, you lose that extra degree of freedom. Compare this to dynamical stabilization rather than pinning it down somewhere it's resistant. Where now we are replacing a static bias with an AC signal into the qubit. What this is going to do is it's going to eliminate the nice, steady time invariant states that you used to have, which when you do computation, and it's going to replace them with moving states that nonetheless are persistent. If you start the qubit in one of these moving states that is predictable, it will remain in that moving state. You can imagine as rotating from the static 0 and 1 state, adiabatically turning on this control signal, and now the new state is a time-dependent state that is predictable and is moving around the Bloch sphere in some way. A really good benefit about these is that they also have sweet spots in their control parameters, just like these do, where they become invariant to flux noise or resistant to flux noise. But as opposed to here, now these curves are continuous. So you can now vary the parameters in a continuous way. You're now free again to modulate the controls on this qubit without exposing the qubit to an area where it will quickly dephase. Or the non-physicist, where it will quickly lose its quantum information. This has been well studied. The sweet spot manifolds of this have numerous experimental and theoretical papers written on them. What we are interested in is what happens when we add another drive with a second drive tone to it and generate sort of a double Floquet qubit. Now, this is more than just generalizing this to a second dimension. As the physicists here are aware, adding a dimension to the problem does more than just double the complexity of the problem. It changes the problem completely. This new degree of freedom allows for dynamics that are 2D in nature, that are that have no analog in the 1D case. The second pulse doesn't just add 1 degree of freedom, it actually adds 2. Because not only do you have now the mixing angle, the relative strength between the two drives, but you also have the second drive frequency as a multiple of a base drive. And we will see that not only are the values of N1 and N2 significant, but the value of the base frequency also is very significant in determining the sweet spot manifolds that will emerge. Now we go in a little bit more technical, but what do we mean when we're talking about these moving states? So if we have a time-dependent Hamiltonian, but it is periodic, from the theory of differential equations, we get Floquet's theorem, which tells us that the corresponding Schrodinger equation will no longer have steady states, but it will have quasi-periodic Floquet states, where this is now a t-periodic vector, and this is an observable gauge invariant quantity called the quasienergy. And let me stress, this is not some artifact of a moving frame. This is a real effect. It is observable. These are the spectral lines of a manufactured Floquet qubit. You can measure, you can see it in the lab. The other thing that I want to point out, because it will become relevant later, is that this is a qubit, even though there are many spectral lines. So 2 levels, but many lines. And this is because this variable here, due to the periodicity, is the quasienergy is only defined up to multiples of the driving frequency. And if you look, all these diamonds are exactly the same. They're just shifted up and down. And if you were to take a ruler, measure it, make the right conversions, you would find that the distance that these are shifted are exactly 1 drive frequency.
So the phase factor, the quasienergy phase factor, presumably that is not t-periodic. Is that also t-periodic?
It is, this quasienergy phase factor is 2 pi over t periodic. It's not really that different from just measuring phase in general, because you once it like completes 1 cycle, be able to measure anything, but it's value modulo the full cycle.
I understand that.
Yeah.
I just wanted to know when u alpha t gets back to original vector, does that phase factor become?
So shift t by t. Yeah, it will not. And these are misaligned.
Yes.
And this is why this is not, I didn't say that this was a periodic vector. It's not a periodic vector. It's quasi-periodic. Yeah, there's a mismatch there. But yes, good observation. So in the basis that is spanned by these orthogonal time-dependent vectors, you get what is apparently a time-independent system once you've transformed into that basis. And your new computational basis vectors are those u alpha, and you can do quantum computing as per usual, but now in this frame. Moving to 2 drives, we define this Hamiltonian, and we are using the flux qubit convention, where we have switched the poly z and the poly x vectors. Just for consistency in the literature, you can just flip them back in your head if you wish. But we have a bichromatic Hamiltonian, p-periodic, where for every Floquet mode, we are able to define a time-independent problem by considering the Floquet Hamiltonian. The quasi-energies and the Floquet modes are eigenvalues of this Hamiltonian. And once you have defined that Hamiltonian, it becomes a eigenvalue problem. In this rotating frame, in the proper rotating frame, it becomes a time-independent eigenvalue problem. So what is that correct frame? How can we find that correct frame? It can be cast, you're cast to a fully time-independent formalism by re-representing your basis vectors in terms of the atomic states, which were the original time-independent states of the qubit before the drive, and the T periodic Fourier basis. These satisfy the product of these vector and this function satisfy all the properties of a tensor product space. So we just take that series, define the tensor product space, and we represent the Floquet Hamiltonian in this space. This is equivalent to taking its Fourier series. It's basically what we're doing. We're taking Fourier series of all of our vectors and have transferred the time dependence over to our basis vectors, and the coefficients are now time independent. When we do this, the Floquet Hamiltonian splits nicely into two terms, which I call HQ and HC. Where HQ is diagonal in the drive harmonics, whereas HC, which I call H coupling, induces transformations on the Fourier basis according to raising and lowering the harmonic by a multiple of the drive frequency. The Floquet Hamiltonian, these two also have the very nice property that they have a very clear interpretation. This, if you'll notice, is just tensoring with a diagonal basis, which is doesn't really do anything to this space. But this is just the energy of the original qubit under bias B. This, on the other hand, contains all of the information from the time-dependent AC signal. So HC quantifies the role of quantifies the influence of the AC signal, while HQ quantifies the influence of the qubit you originally had.
Mathematically speaking, you make a separation of variables.
Pretty much, yeah. And this, by putting this into the time-independent frame, you really cleanly see which terms are due to what you used to have, and which terms, or when you used to have before you changed on the time dependence, and which terms you obtain from the AC drive. This splits our analysis into two regimes. The regime where the bare qubit dominates and the influence of the time-dependent drive is treated as a perturbation, and the regime where the drive dominates and the original qubit is treated as a perturbation. We call the regime where the bare qubit dominates the weak drive regime, and the strong drive regime for obvious reasons. Now remember, I was talking about these sweet spot manifolds that will emerge and we're about to see. According to the literature, and this is a very reasonable assumption, the dephasing rate, which is what we are trying to minimize along these high lifetime curves, are roughly given by the response of the circuit to variations of the bias times variations. Oh, this is the wrong symbol. This is supposed to be a B. Times variations in the bias plus variations, the response of the circuit in variations to the drive amplitude times the variation of the drive amplitude. A very natural assumption. The dynamical sweet spots occur when you become first order invariant to variations in your bias, in your first order invariant DC noise, which makes sense because the noise is going to be dominated by DC noise due to the 1/f noise. There's also in the Floquet literature the concept of the doubly sweet spot, where the time derivative or the derivative of the gap with respect to the drive amplitude also goes to 0. And the literature predicts that when both of these conditions are satisfied, you will have your optimal working points. We will be challenging this notion later. Let's start by analyzing the weak regime. We have an unperturbed system, HQ, and we treat the time-dependent drive terms as a perturbation with now defining perturbation parameter omega over my bare qubit strength. In the weak regime, the avoided you obtain minimal distance or avoided crossings between the levels whenever you satisfy this resonance condition with the bare qubit gap. In other words, when your drive base frequency times some multiple will be resonant with your qubit transition. So if you were to pick, for example, L to be equal to one of your drive multipliers, N1 or N2, then you would have one of your drives effectively driving Rabi oscillations in your bare qubit. In the weak drive regime, the lifetime manifold depends strongly at L, N1, and N2 at the avoided crossings, first condition. And the second condition is that you want to be an avoided crossing. Because as you see here, away from these avoided crossings, you have pretty much a linear dependence on the relationship between your bare qubit frequency and your driving frequency. And the bare qubit frequency is linearly dependent on your bias. So away from these locations, you get a linear dependence on static DC flux noise. And you see here that even though we remain in the weak regime in both of these cases, the sweet spot manifolds look very different just by picking different multiples L, N1, and N2. One of the things we found is a condition on what variables L, N1, and N2 you should pick. Now, for on-resonance driving, we obtain through perturbatively this expression to first order in our perturbation parameter. And the thing to notice is that this expression is linear in the DC bias. Therefore, at no value of the mixing angle nor the drive strength will you get anything but a linear dependence on your bias variable, and there are no sweet spot manifolds, as seen here, where this quantifies the lifetime of the qubit. It's pretty much bad across the board. Makes sense. However, when you're off resonance, but a higher harmonic of your drive is on resonance with the bare qubit gap, you restore the sweet spot manifolds. And we believe that this is because to first order it in the perturbation parameter, you get a quadratic dependence on the bias, which is, of course, first order invariant to small fluctuations. So as long as this condition is satisfied, at every flux point where the DC qubit would have been resistance to flux noise, your new Floquet qubit will also be resistant to flux noise along these sweet spot manifolds. The strong regime, the dependence on the relationship between the drive and the bare qubit is much less pronounced. There are still very different manifolds that arise from choosing different L, N1, and N2. But we find that pretty much across the board, you will always have sweet spot manifolds and similar strength or similar lifetimes across all of the conditions. Now, to some open questions which challenge some preconceived notions that exist in the literature. How am I doing on time?
Half an hour.
The open question, the ones in which you hope to give a contribution in your thesis?
Among them, yeah.
But I want to say, all of what you presented up to here is standard, or there is something that came by your research?
Oh, up and
Up to now,
well, the characterization of the manifolds in
yes.
terms of the driving frequencies and these plots basically as well. Those haven't been shown in the literature for a bichromatic drive in terms of these parameters. I mean, it's easy to just look at the plot and say, okay, you made a plot. The amount of work that went into doing these simulations, optimizing there were numerous instances where we found that the Floquet object that everybody had been using actually made mistakes and required optimizations and corrections to get these plots. So there's a lot of that I'm not glossing over right now, work and contributions that went into finding these manifolds. Also, the method that we use to derive these expressions, this perturbative calculation, had never been done for a bichromatic drive. It's significantly harder than doing it for a monochromatic drive. But yeah, I would say the main contributions that are relevant for an experimentalist are finding conditions at which your L, N1, and N2 give good lifetimes. And these perturbative calculations, which can give an idea of what gaps to expect. Of course, experiment ruins everything. It gives a ballpark. Oh, something else I think might be interesting to mention is that I think the weak regime results are a lot more promising than the strong regime, even though if you look at the at this axis, the strong regime has lifetimes 1 order of magnitude higher, and the manifold on this side, which is the quasienergy gap, sorry, I forgot to mention, has more variation. But when you factor in experimental non-idealities, you generally don't want to be pumping too much energy into your fridge. And the strong regime definitely is pumping at all times a strong radiation field into your fridge. So if you can get away with weak driving, you generally want to get away with weak driving. All right, open questions. The famous doubly sweet spot, which I suppose the question now is the doubly sweet spot a myth or just mythical and rises under certain conditions? So I'm missing an expression. And that should be a delta B, and I'm also missing wherever it goes to control mechanism.
Computer at the delta.
It's okay. I will explain and possibly on the whiteboard say what this variable and this variable is. But recall that in the literature, this expression occurs all over the place, including from experimental groups, which are generally much more married to realistic and reasonable assumptions. And the claim was that when both of these terms independently go to 0, will be your optimal working point. However, even in the literature already, there was some contradictory statements. In particular, we know that this derivative should be proportional to this variable G05, which should have been here, but I will put here. So G05,
Our next slide by chance.
check. I think I can just explain it verbally. I don't even have to write it down. No,
Oh, okay.
no, it disappeared. G05 is the response of your circuit to 0 frequency noise. So in the same way that you can take the Fourier series of your qubit, of your Hamiltonian, and get the Floquet Hamiltonian, you can do a similar procedure with your noise. And then you separate your noise into its spectral density, which tells you at each frequency how much noise do you have. If you combine this representation of the noise with open quantum system theory, with the master equation formalism, you are going to get that your dephasing rate is going to be equal to the product of the noise at some frequency times the system's response to signals at that frequency. The response to signals at 0 frequency is G0 phi. But if you think just back to calculus, what is the response of a system to a push? It's derivative with respect to whatever you're pushing. So this relation makes a lot of sense. In the same way, this, which should be a B, would quantify how much you're pushing the 0 frequency noise. So it makes sense that it will be the spectral density of the noise at 0 frequency. So what I have done here, yeah, this is an earlier version of this slide. So ignore this, pay attention to this. What I have done here, so for those on Zoom, ignore the upper diagram and just pay attention to the lower diagrams, which I'll be referring to right now. What I have done here is I have plotted this variable G0 phi. And we find that it's pretty much just this that determines the sweet spot manifolds. Moreover, plotting the numerically calculated gradient of the gap of the qubit frequency with respect to variations in the qubit and the drive strength show pretty much no correlation with the lifetime manifold. In fact, we see that in some locations, we have effectively a slice taken out of the sweet spot background at locations where this derivative goes to 0. So there's some strange effect going on here, which I don't quite know how to explain. I have suspicions though. I suspect that this would have a greater influence if it weren't for the fact that 1/f noise is dominant. In almost every application, 1/f noise is what's going to dominate your the spectral profile of your noise. If we were to use a different noise model that incorporated more instrumentation noise or more variance into the amplitude and mixing angle of the drive, would we see a different manifold appear? Would we see doubly sweet spots emerge? That is a numerical simulation that I am working on right now to see, is the doubly sweet spot just hidden by our noise model at the moment? Or is there actually something inherent about the qubit that makes it mostly invariant to noise in the amplitude at the sweet spot manifolds? Let's say that it is our noise model, and we are just not incorporating enough instrumentation noise into our simulations right now to see the double sweet spots. Are they experimentally relevant? Well, what is the most realistic noise model? Preliminary searches in the literature suggest it's going to be a hard question to answer because there isn't a lot that is studied for noise that is at these like higher microwave frequencies, which are the harmonics of the drive. Right, our Floquet qubit will be sensitive in theory to noise at all harmonics of its drive. So that is also an open question that we will be working on answering. What is, if this is just an artifact of our noise model, what is the actual realistic appropriate noise model for this sort of qubit? The second, which I think is a more confusing problem, at least for me, are these sour spots. These are the same diagrams that you had seen before, but a different parameterization. where now instead of varying the total amplitude and the mixing angle, I am just varying the amplitude of the two drives independent of each other. It is the same simulation, just a different way to vary the parameters, a different way to graph. The reason that I chose this parameterization for this is because it highlights regions that I call sour spots, which are anomalous cuts in the high lifetime manifolds that emerge at locations where we would have predicted from our perturbative analysis would remain high lifetime. Previous literature gave a derivation of the fact that the width of these lifetime manifolds is proportional to the size of your quasienergy gap, which explained these cuts, because these cuts emerge at avoided crossings where it's barely an avoided crossing, where your spectral lines basically touch and your gap goes to zero. At these locations, you get a pinching of the manifold and your lifetime hangs. And it makes sense. But we observed this pinching behavior not only at the minima of the gap, but at the maximum of the gap as well, at both extremes. So that proportionality relation, it doesn't really make sense. And we had previously noticed that talking about minima and maxima of the gap is a little misleading because the quasi-energies are defined only modulo multiples of the driving frequency. So when you would maximize this avoided crossing, this gap, you would actually be minimizing another gap on top. So is it in fact proportional to the smallest of the two? That also fails, because generally this gap will always remain much bigger than this gap. So something else is leading to this structure where you have anomalous cuts in your lifetime that is not a direct proportionality to the size of the gap. And if anybody has any ideas as to how this is happening, I have been pulling my hair out over this for, I think, 6 months at this point, which is very little in the term of research, but to me feels like an eternity. So in conclusion, we have analyzed the lifetimes and spectral properties of a dynamically stabilized qubit using a bichromatic. And we observed that in this case, most of the high lifetime curves occurred in places where both of the drives were non-negligible. Therefore, the bichromatic effects were very significant in determining the high lifetime. Split our analysis into two regimes, the weak drive regime and the strong drive regime. For the weak drive regime, we derived conditions at which you can expect to find high lifetime curves and conditions where you expect the lifetime to be bad across the board. And for strong driving, we find that the conditions are less strict. You will still have different properties of the manifold at these different resonances, but generally you can expect to find high lifetime curves across variations in these parameters. In both regimes, we found that the high lifetime curves cross regions where the gap varies significantly, which is important because one of the reasons that we wanted the bichromatic effect of the bichromatic Floquet qubit is so that specifically we could modulate this frequency using our control parameters. And the fact that it crosses regions where the derivative of the fact that these curves cross regions where the derivative with respect to the control parameters is high suggests that we will be able to find regions where we can we can make rapid modulations of the qubit frequency without exposing our qubit to environmental noise. Finally, we found that the sour spots occur at both the minima and the maxima of the gap, which challenges the current stance of the literature that the width of these curves is proportional to the size of the gap. There's a more sophisticated effect going on here. And that is all I have.
Very nice. Questions from our
I
audience?
have a question for you. Well, maybe it's out of your interest, but connected to quantum algorithms, right? We know that quantum algorithms, they suffer from the coherence problem.
Yes.
And also because they were proposing like bigger elements, different than nanoparticles, nanocomponents. It seems to me that it would be more, I mean, not available, but somehow more friendly to applying the quantum algorithm that you know. We know very few of them. I don't think you were going to find new ones just by looking at this kind of a work, but maybe to apply, I mean, this when they are ready for making a computer, the quantum algorithm. You have any idea about that?
How to
I mean,
apply?
how would they be more friendly or feasible to application of quantum algorithm that they are the most important part of quantum computing?
Right. So there are. This would be one tiny piece of the puzzle at making that possible. Generally, you will not get error-free quantum computation to happen. I don't know. I was going to write something, but you get away without math. Generally, you will not get noise-free qubits. You will always have some noise that would, in theory, ruin your computer. However, there are error correction protocols that rely on surface codes that will, if you are below a certain threshold of error, they will allow you to correct these errors. And that is the only reason why we think this is a realistic pursuit to build a quantum computer. This is a method to get your qubit below that noise threshold while still maintaining flexibility and tuning the parameters of your qubit. This is going to become especially important as we scale up, because as you scale up, any system that's bigger in size is going to have components that are, the variance is going to become more significant as we scale up in size. Because at least one of your chips, it's going to become harder and harder to manufacture that many chips that are that close to your parameters. So by constructing essentially configurable qubits, it gives the manufacturer more flexibility, as well as giving the controller, the experimentalist, more flexibility in lowering the noise threshold so that you can use these error correction codes. As far as actually using algorithms on these qubits, once you find your Floquet states, you can generate, mathematically, you can create a basis out of them. And then you do your math and you design your Chrome protocols in this new time-independent basis. And all you have to do is, before you send it back into the computer in the cable, you just need to apply the correct rotation. So the control protocols essentially rotate with the qubit. So there isn't really, we have, I didn't show in this presentation because there's no time, but we actually have ran gates on these, simulations of gates on these qubits.
New gates.
No.
The old gates doesn't
Yeah.
really represent it.
Yeah. We are not, so my group is not at the level of like large scale algorithms. We are still, neither is quantum computing really for that matter. We're still trying to like create reliable basic operations that have been known for some time. So this is at the level that we are operating. Once we get it though, these building blocks will be able to quickly come together to form these larger gates. Yeah. Another thing, so sorry, to go off of that, with time-dependent protocols, there are also protocols that allow you to disentangle two qubits, or even by modulating their frequency and making them more separated, which again is a significant problem as we scale up crosstalk between these qubits.
So on your last point, it seems naively like you should be looking for something that's related to the rate of change of the energy gap, because that goes to zero with the minima and the maxima. I assume you've already looked at something like that. Did you say
Yeah,
you
we
spent 6
did,
months?
and again, like I was really excited when I got the simulation to work because I was like, okay, great, now I'm gonna, or more like when I found the package that took the derivative of this manifold for me. And, nothing. And if when I ran it for this plot as well, nothing. There's If there are locations where they line up, yes. But to me, it looks more of a, they both depend on the same thing than one causes the other.
Of course, you can imagine a lot of things that you said completely escaped to me because it's not my job. But I have two questions more in my role of MPP director than in my role of Marco Banza. The first one, there is a clear experimental component here in order to use us.
Yes.
My worry is, do you find here in Chapman MPP in physics the tools to realize that? So you have in the good environment for that, you need help from us, can we help into, because MPP is more a theoretical program. So I am a little bit worried that we are not able to provide you with all you need on a more material aspect of it.
Yeah, there is a solution. My bad manners actually probably led to this question because I did not also introduce all the other teams that we work with. We work with in very close collaboration with Berkeley, who actually have these things in their bridges. And so basically we are the theory support. We are on a grant where we are theory support for them as they try to build.
I want to say that in the limit of the possibility, if you need financial help by MPP, you can, I cannot say you will have, I say you can ask, and then we will see what we have. But do not, I think that is part of us to try to put our students in the best situation. So if we can provide help, we are here for that. Possibly we cannot. In this case, we cannot. We say we cannot. But
I mean, trips to Berkeley are always very productive.
okay. In any case, I wanted to be clear about that because it's clearly a research that has not only intellectual aspect. Of course, there are a lot of intellectual aspects, but not only that. And the other aspect is what are, and if there are, I think that certainly there are, and what are the in which time the impact of research can have on a technological aspect. So you think that the way in which you can solve or not solve, on better describe, on better identify the open problem can really help to construct, to produce in a certain short time better artifacts.
Yes, I mean, this just visually, these manifolds are much richer and actually entire lifetimes than were possible with just one drive. So that's kind of like the yeah, it's a contribution just by finding ways to control these bichromatic qubits. More generally, it takes an army to build these things. And I am part of the discourse here that is generating basically the environment in which these technologies can move forward.
And legally,
right now, quantum computing is at a state similar to what AI was right before it's the AI winter, which is very ominous. But it's ominous and promising. Ominous because the AI winter happened, promising because the technology is developing at a pace similar to what it was then, and the goal is at a distance similar to what AI was then. So I think I might be old, but I'm hopeful that within my lifetime I will see it.
And legally speaking, you are in a situation with all these contributions are covered by copyright, correct? Chapman will give you the right. I don't know. I have no idea what does it mean legally, but certainly there is a legally aspect of all that.
I don't think there really is a copyright interest in our field right now. We're all just pulling our hair out and desperate for any answers. So
also on this side, I want to say, if you think there is a need to do something.
Not for what we're doing.
No.
There are corporate interests like Google and IBM, but what we're doing, it's all in the academic sector.
Okay.
Yes.
per se.
If I was presenting an internship project, I'd probably be a lot more tight-lipped.
I have a question following up on what you just said. You said you hope to one day experience a quantum computer. What is the threshold for which you're defining a quantum computer, given that Google has quantum computers with 100-ish qubits that are fully operational, right?
That is a good question because it demands a level of nuance to what you define. And I think to accurately answer, I have to give like a similar scaling. I think I would be very excited to see quantum hardware become a important part of, for example, nanoparticle design in drug manufacturing, which is a much closer goal than breaking up cryptography and ending the world. Which is what some people would have you believe is the reason for quantum computing. I think that it's, for me, honestly, I think it's a more exciting goal. It has more benefits to be able to understand, design things that happen at these levels that we simply cannot model right now because the overhead for the full quantum simulations is so high. This is already happening. As you know, there are already, quantum hardware is already being used, but to see quantum hardware become the dominant method for studying these systems, I think that would be something that would make me very happy and excited to see in my life, and I think is reasonable. As far as full-scale quantum computing, I am going to say something a little sacrilegious. I am not that excited about Shor's algorithm, honestly. Yeah, it breaks encryption. There are also ways to fight it. I mean, working on these things, I can tell you the complexity of adding just a few more registers. So if you can build a quantum computer that can break a something bit key, add 1,000 more bits, and you're gonna have to wait another 50 years for the hardware to have it up again. Of course, that could be wrong, and there could be some developments that I cannot foresee that will allow these things to scale up massively. But I am excited, however, about actually, there have been even recent results on methods for solving huge systems of linear equations with quantum algorithms. And solving huge systems of linear equations is a little applicable to most fields. Yeah, pretty much everything, if you decompose it correctly, becomes a huge set of linear equations. Almost everything.
Except when the nonlinear equations.
Except for nonlinear equations, then you take derivatives and you study like the. So then, not for non-linear equations, then you use differential quantum geometry to zoom in, and then you have a system of linear equations again. Roughly speaking, I don't think the theorists do that as much, but definitely the applied scientists. Everything has to be linear. So I think that, for me, would be the final goalpost, to see a quantum computer, because that has similar demands on it as Shor's algorithm, to see a quantum computer be used, for example, to create extremely accurate weather models. I think that would, for me, be the final finish line.
Fluid dynamics is tough because often it is nonlinear.
Yeah, which, the stuff that I read basically made it sound, and I'm not an expert in this, so it could be wrong, made it sound like the solution to that in their numerics right now is they just add more linear equations to simulate the nonlinear terms. Again, I don't know much about this at all. But.
Right. Any final questions? Any questions on Zoom? Let's thank our speaker.
Thank you.